Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler and today we're going to be doing Unit 7, Lesson Number 3, More Work with Related Rates. So this is our second lesson on related rates, and remember, in our first lesson we basically laid out the fundamental ideas for related rates, right? The idea that we express a rate as a derivative with respect to time, right? We identify the rates that we have been given, the rates that we know. We identify the rates that we are after, the rates that we're looking for. And then we create a linking equation between the two fundamental or three fundamental variables in the problem. All right? What we're going to be doing today and in the next lesson is looking at some of the, if you will, classic problems in related rates. These will illustrate an approach more than a specific type-by-type problem, but there are some classics that sort of every student experiences. So let's get into those today. All right. Shadows. I love shadow problems, because I love walking down the street, listening to a cart go by in the hallway. Now, walking down a street right at night and you've got a street lamp behind you and you see your shadow out in front, right? And your shadow plays by particular rules, and we're going to see those in the first problem. So let's take a look. We've got a person who's 6 feet tall and is moving away from a lamp that's located 20 feet above ground level. The person is walking at a rate of 3 feet per second. How fast is the shadow growing? All right, let's not worry about rates that we want, rates that we know, anything like that. Let's just get a feeling for this problem. Let's draw the person. Well, actually, let's draw the ground. All right, we're going to assume that's level ground. Let's draw a street lamp. Strangely enough, my street lamp is going to look a lot like my person because I only draw stick figures. All right, so we'll live with it, right? What do we know? We know that this distance is 20 feet, and this distance is 6 feet. What do we know? The person is walking at a rate of 3 feet per second, right? So we know they're moving along here. There's our rate. We'll have to figure out what that's a rate of. And where's the shadow? Well, the shadow is formed because light gets blocked, right? So if you will, the shadow is right in here. That's the shadow. All right, so we're interested in how fast the shadow is growing. All right. Now, a lot of students will look at this and they'll immediately start thinking about the Pythagorean theorem because it appears that there are right triangles involved, and there are. But first, we just have to start to get some rates that we know, rates that we want. All right, so let's just make sure, all right, that we can really get a feeling for this 3 feet per second, right? We have to write that as a rate. But the question is, what is it? It's the change in a length, right? Feet per second, but what length? Pause the video right now and think about what length d what dt, right? That's the question mark. D what dt equals 3 feet per second. Pause the video and think about that. All right. Believe it or not, it could be many different distances. But probably the easiest one to think about is this distance. I'll call it x, right? So in other words, I can get rid of that question mark now. We know that that length is getting longer at 3 feet per second. Comfortable? Now let's figure out what we want. That one's actually easier to figure out, right? We want to know how fast his shadow is growing. So we want to know this, right? If we take this length, sorry about this arrow here, we want to know ds dt. So somehow we now have to relate this length to this length through something. And again, people's natural inclination is to try to do it through a Pythagorean theorem, but that really doesn't help very much. It doesn't bring in the 20 or the 6, and I really don't care about the hypotenuses on these triangles. So pause the video now and see if you can think of any geometric tool that you could use to set up any kind of an equation that relates x to s. Pause the video now. All right, this is actually quite challenging for a lot of students because what you have to use is similarity or similar triangles. So what I'm going to do is I'm going to take this picture, I'm going to just draw it down here, and I'm just going to do a snapshot of time. Okay, sorry about how poor it looks. Right now I know this is 20, and I know this is 6. I know that this is x, and I know that this is s. But because they're both right triangles, and because they both share this angle, these two right triangles are similar. Right? Remember this symbol from geometry? They're similar. And therefore you can set up ratios, right? Now, one thing that's key is that we're talking about the similarity of this big right triangle, whose base is x plus s, and the small right triangle here. So I can set up a lot of different equations, The one that I'm going to go with is s is to 6. So if I take this side and I divide it by this side, I will get the same as x plus s, this divided by 20. And that's it. That's the equation that relates s to x. And of course what we're going to do next is we're going to take its derivative. Now, nobody ever said, though, that you couldn't play around with the equation before you bring the calculus in. So although I could certainly take the derivative of this implicitly with respect to time, what I'm going to do is I'm going to manipulate it a little bit. I'm going to bring the 20 up here, and I'm going to bring the 6 up here, and be careful to distribute. This, of course, is going to be an easier equation to deal with, but I think I'm going to actually just bring all my s's to this side. I'll leave all my x's on this side. And now I think I'll take the derivative. And now this is really easy, right? Because when I take the derivative of the left side, I get 14 times ds dt, and the right side, 6 times dx dt. All right, remember, we know what dx dt is. It's 3 feet per second. So I can now say that ds dt, if I bring that 14 to, oops, that was weird. That's what happens when I try to write and talk and do all this at the same time. You bring that 14 over to the other side, right? I can substitute in my 3 feet per second, and when all is said and done, we get some ugly fraction, 18/14, which isn't very helpful to me. I like 1.286 feet per second. That should have had a C at the end of second. What are you going to do? I guess what I'm going to do is put one in. All right. That's kind of cool, isn't it? One of the things I love about this shadow problem is notice that it doesn't depend at all on how far the person is away from the lamp. In other words, that shadow is going to grow at 1.286 feet per second as long as the person is walking at 3 feet per second, which is kind of cool. It means that the farther you get away from the light, the longer your shadow will get because it's always growing. And it's always growing at that rate if you're walking at 3 feet per second away from the lamp. All right, I'm going to scrub out the text, so copy down anything you need to. All right, here it goes. Let's move on. All right, moving perpendicular. So there's many situations where you have two objects that are moving perpendicular to each other. All right, so think about them like this and moving along these perpendicular lines, okay? And let's take a look at a classic scenario. We've got two cars, car A moving at 50 miles per hour and car B moving at 60 miles per hour. And they travel north and east, respectively, from an intersection. How fast is the distance between them changing when car A is 30 miles to the north of the intersection and car B is 40 miles to the east of the intersection? Again, before I do anything with rates that I know and rates that I want and all that, I have to get a feeling for the physical situation that's going on. So let's orient ourselves with maybe a little compass orientation, right? Something like this. Right? Maybe we'll have north and east. Okay. Two cars. Car A is moving north. All right. And we'll just put a little A here. Moving north. Car B is moving. All right, car A is moving north. Car B is moving east. Right? And we want to know how fast the distance between them. Oh, that was terrible. I'm just going to add it. And then I lost some of my axis. We want to figure out how quickly the distance between them is changing. I'm going to actually try to use my line here. All right, so I want to know how fast that distance is changing. Okay, so we actually kind of know what we want. But we have to think about our rates, right? Now, what are we doing exactly, right? We know that the car A is moving at 50 miles per hour. That's one rate, right? 50 mph. And we know B is moving this way at 60 mph. So what I'd like you to do is pause the video and try to write those two in terms of derivatives of quantities that you label on that picture. Always label quantities on the picture that you're modeling. All right, well, there's lots of different ways you can do it, lots of different variables you can choose. Because of the resemblance to the xy axis, I'm going to call this x, I'm going to call this y. Right, so I know that dy dt is equal to 50 miles per hour. I know that dx dt is equal to 60 miles per hour, right? And what I want is that. Now, I'm going to be very suggestive here. I'm going to call it C, all right? And I want dc dt. Right. That's what I'm looking for. So why don't you come up with an equation that relates x to y to c? All right, I hope you thought Pythagorean theorem. It's a great example of the Pythagorean theorem, right? If I take that x distance and I square it, take the y distance and I square it, I'm going to get the hypotenuse squared. You could solve this for c if you wanted to, but it would interject a square root into the problem that's not necessary. In fact, right from this point, we can certainly take the derivative of both sides with respect to time. Many times I don't even show this step, right? And we'll get 2 times x times dx dt plus 2 times y times dy dt equals 2 times c times dc dt. Now, most of the time at this point, I just cranked stuff in. But at this point, what we're actually going to find is some things are missing. And let's kind of identify what we have right at this point. Okay, I'm going to use red. Do I know the value of x? Let's see. X would be 40 miles, right? So I know that. Do I know dx dt? Yeah, there it is. Do I know y? Yeah, it's going to be 30. Do I know dy dt? Yep, right there. I'm looking for dc dt, so the fact that I don't know it is very reasonable. But I still don't know what c is, right? I don't have that value. So how am I going to find it? Pause the video right now to think about this. This is important for many of the problems we do today and tomorrow. We're going to use the linking equation. Almost always, if we have a missing value of a variable, not of a rate, but of a variable, we will go back to the linking equation. So in other words, I can come right in here and I can say, oh, all right, well, when x is 40 squared plus y is 30 squared, I'll get the value of c squared. I would hope actually that many of you would realize that this is a famous 3, 4, 5 right triangle, and c is 50. But now we can use that to finish the problem. I'm going to go back to blue. We can say 2 times x, which is 40, times dx dt, which is 60, plus 2 times y, which is 30, times dy dt, which is 50, equals 2 times c times dc dt. I'm not going to go through all the algebra, but what we'll find, because there's not much left, is we'll find that dc dt is a whopping 78 miles per hour. Right, obviously that means it's growing. Now that's not a big surprise because what's happening is that they're both kind of stretching out. But you could imagine that if one of them was traveling in one direction and the other was, let's say, heading south instead, then that distance may either be getting longer or getting shorter, depending on the relative speeds of the two cars. All right, so I'm going to clear out the text here. Pause the video if you need to. All right, here it goes. Let's go on to the next problem. The cone. Everyone has to do a cone problem. So here we go. Water runs into a conical tank at a rate of 9 cubic feet per minute. There's your rate, right? There's your derivative. The tank stands point down as shown below and has a height of 20 feet and a base radius of 5 feet. Fair enough. Notice on the picture it's shown as the diameter. How fast is the water level in the tank changing when the water is 6 feet deep? Note that the volume of a cone is given by that equation. All right, so let's kind of visualize this. All right, understand what's going on. We've got water that is pouring into this tank at a rate of 9 cubic feet per minute. All right, so it's filling this tank up. I'm gonna like draw the water inside the tank. Okay, so that water's filling up. Okay, it asks us then, how fast is the water level, this term, the water level in the tank changing when the water is 6 feet deep? What does that mean, the water level? It means the height of the water, right, or the depth of the water, all right? Now, this is the most confusing thing about cone problems, all right? So I'm going to explain the most confusing thing right now, and I want you to keep your eye on this ball throughout the entire problem. There's actually two cones in this problem. There's the big cone that is holding the water, and that's a static cone, right? That cone that's 20 feet high and 10 feet in diameter. And then you've got the cone of water that's actually changing inside, okay? That's the thing I'm gonna put variables on. So in other words, this cone of water has a height of h, and it has a radius of r, right? So what do we know? How do we translate this thing as a rate? Pause the video and write down a rate as a derivative. All right, let's do it. Hopefully you realize cubic feet is volume, or our volume units. So dV dt equals 9 cubic feet per minute. But be very clear about the volume of what? Specifically, V is the volume of water in the cone. Volume of water. All right, it's not the volume of the overall cone, right? The volume of the overall cone isn't changing, and we don't really care about it. And what we want, right, is we want dH dt. All right, so at this point what we always do is we always have to come up with a formula that relates V to H. But they've given us that. That's what we have right here. All right, so that's our linking formula. V equals 1/3 pi r squared h. All right. Now, there's a problem here. You know, I'd like to launch in and just take the derivative with respect to time, but there's a problem. What I'd like you to do is I'd like you to pause the video, and I really want you to think about why we can't really, I mean, we could take the derivative, but we would run into a problem. And what would it be? All right, here's the problem. The problem is, if we take the derivative of this volume formula, we'll have to use the product rule. And in the product rule, we'll both have a dH dt, and we'll have a dr dt. But we don't know dr dt. So that's one too many unknowns. One too many unknowns. All right, now there's a few different ways around this, but there's kind of a classic way of doing it, and that's what I'm going to show you. I'm going to slice this cone right now. I do it with red. I'm going to do this, and I'm going to pull that out. Pull that slice out. Because what a cone is, at the end of the day, is it is this type of cone, a right triangle that has been spun around a vertical axis. Okay, the way that it's oriented right now. So I'm only going to look at that triangle. And here's what I see about the triangle. I know that that's h. I know that that's r. I know that this is 5. And I know that this is 20. So what I can do is I can actually establish a relationship between r and h. In fact, using similarity again, I can say r is to h as 5 is to 20. And I'm going to simplify that down a little bit to 1/4. Okay? The reason I want to do this is I really don't care about r. I'd really rather it not be in the equation at all. And in fact, what I can say is that r will always be 1/4 h. So as the water is filling up this cone, the radius at the top of the water, the radius of the water, the cone of water, will always be 1/4 times its height. And that makes sense because if it's completely full, If the thing is completely full, then we know that the radius is 5, and we know that the height is 20, so the radius would be 1/4 the height. But here's what I'm going to do. I'm now going to take this and substitute it into this formula. All right, go back to blue. So I'm going to get V equals 1/3 pi times, I know it's going to seem dorky, but I'm going to go back to red, 1/4 h, that'll be the last time, squared times h. Now, my great suggestion is to simplify this, right? So I'll get 1/3 times pi times 1/16 h squared times h, and that's 1/48 pi h cubed. Now, I want to emphasize something. I have done this much calculus at this point. Nothing. Okay, besides laying out those rates, I've done nothing. Right now, what's really great is I know the volume of the cone strictly as a function of the height of the cone. And again, I'm talking about the cone of water, not the overall cone, right? So now I can easily take dv dt. All right, that 1/48 and the pi, I'm just going to kind of leave factored out. I'm then going to get 3h squared times dh dt. And now it's all about just filling in values, right? So when h is 6 feet deep, right, that's what they told me, I'll have 1 divided by 48 pi times 3 times 6 squared times dh dt. That's actually what I'm looking for, and all of that will be equal to 9. So look at this. You know, you probably can't even tell that's an h. Let's make it look like an h. There we go. Look at this. The only thing left in this equation to solve for is what I'm looking for. Again, I'm not going to go through that. You're at a high level. You should be able to solve for dh dt. Believe it or not, it actually comes out relatively nice. At the end of the day, it turns out to be 4 divided by pi, but who in the world would want to know that? What I want to know is that it's filling at 1.273 feet per minute. Always think about your units, right? Wow, that is a classic. And almost every cone problem that you ever work on in related rates of change goes something along this lines, because the volume of a cone always depends on 2 variables, the height and the radius. You tend to want to eliminate one of them before ever taking the derivative. And the way that you always do that is by using similarity of triangles, of all things. So look for that. Look for it in homework assignments. Look for it on the AP exam. All right, we're going to clear this out, copy it all down. Gone. Let's tackle the last problem. This is one of my favorites. We've got a sliding ladder. A 5-foot long ladder is sliding down a wall such that its top is moving at 1.5 feet per second. How quickly is the bottom sliding outward when the top of the ladder is 4 feet up the wall? So I made a little video. All right, take a look. Here we go, right? Let's take a look at it again. We got this ladder sliding down the wall. I know, it's not going to slide through the wall. I'm not an animation expert. I'm working on it. It's a learning curve for me. All right, but what's cool is you can really visualize this, right? The ladder kind of moving its way on out. Let's get rid of our video. Let's bring in the actual diagram for the picture, right? So 5-foot long ladder. The top is sliding down at a rate of 1.5 feet per second. How quickly is the bottom sliding outward when the top of the ladder is 4 feet up the wall? Okay. So we got a rate we know, we have a rate we want, we got geometry going on. I'd like you to pause this video, take upwards of 10 minutes and see if you can figure out the answer. All right? Okay, let's go through it. Now, we don't want to be fooled by the 4. The 4 in the diagram almost makes it appear that that's a static measurement, but it's really a snapshot of a measurement. In fact, I'm going to give this distance right here a name, right? No great surprise. I think I'm going to call it y, right? Because then I can say that I know that dy dt is 1.5 feet per second. Now, I made a mistake there. I want you to pause the video and think about what mistake I just made. Did you figure it out? The mistake I made was not including a negative sign on this. That's absolutely critical, right? Very, very important. We'll talk about why in a little bit. Okay. Let's talk about the rate that we want. Let me call this x. That's what I want, right? I want to know how fast the ladder is sliding away from the wall at its bottom. Maybe I even want to know how to make a d, right? So we have to relate now x and y. What equation is going to relate them? Pause the video now. Okay, it's our good friend the Pythagorean theorem. One thing that's interesting about this particular Pythagorean theorem is that part of it is a constant, right? I mean, I've always wanted to do a problem where I actually have the ladder not just sliding down, but also collapsing, you know, like one of those ladders that you can do this with, right? But for now, the length of the ladder is actually constant. So in fact, I can say that x squared plus y squared will always be 25. Even as the ladder is moving, even as it's sliding along, that will always be true, which is wonderful. It's wonderful because now it allows me to solve, right? I'll take the derivative of both sides. I'll get 2x times dx dt plus 2y times dy dt. Now be careful of this. The derivative of 25 is 0. That's really critical. Let's take a look at what we know and what we want. Do we know x? No, actually we don't know x, right? So at the moment in time when we want to know what's going on, we know y, right? What is it? It's 4 feet. We know dy dt, it's negative 1.5 feet per second. We don't know dx dt, that's okay, that's what we're solving for, but we need x. So what's x? Yeah. Using the linking equation, we can figure out that x is 3, or using just the Pythagorean triples, we can say that x is 3. So let's substitute it in. Let's put in 3 for x. We'll stay in red for right now. We will put dx dt down because that's what we're solving for. Y we know is 4 at that moment in time. Dy dt, negative 1.5. That's all equal to 0. Solving for dx dt, again, skipping the intermediate steps. Hopefully you're okay with that. We would find to be 2 feet per second. Now, real briefly, I just want to highlight something. If for some reason we had left the negative off here, then it wouldn't have shown up here. And what would have happened is that a negative would have been introduced in our answer down here. Now, again, why would that have been a real problem? Hopefully, you realize that it's a problem because if a derivative is negative, it means that the quantity is decreasing, right? Now in this case, x is a length. It's the length of the base, the length that the bottom of the ladder is away from the wall. And clearly, as the top falls down, that distance is increasing. But if we had forgotten the negative on the dy dt, we would have actually found, counterintuitively, that as the ladder fell, this point, its base point, would actually have been getting closer to the wall. That's what that negative would have told us, which is obviously wrong. All right, so we get rid of it. I'm going to scrub out the text, write down anything you need to. Okay, here it goes. All right. Well, that was our second lesson on related rates of change. We'll do one more of them, and then that'll be it. 3 and done. It's a tough topic. Lots of modeling, lots of specialty problems. Similarity shows up, both the cones and the shadows, so watch that on the homework. But thank you for joining me. This has been another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.